The universe isn't just empty space. It's more like a fabric that bends and stretches and vibrates. That vibration, that bending, it dictates everything. The orbit of planets, the flow of time itself. There's a clue from the physicist John Wheeler. He said spacetime tells matter how to move, and matter tells spacetime how to curve. So we're looking at these theoretical blueprints, 25 of them. They're attempts to describe this architecture, the architecture of reality. By the end, you'll have a kind of master key to the cosmos's deepest secrets. These models explain black holes, other dimensions, the origin of everything. Some theories say space is an illusion, that it's a hologram projected from a distant surface. Others propose it's woven from threads of pure information. What single idea about reality are you most ready to question? The most familiar distortion starts with geometry, a canvas, but it's not a static stage, it's a fabric. Albert Einstein gave us that over a century ago. He said gravity isn't a force, it's a consequence of shape, the shape of space and time woven together. Space-time, picture a taut rubber sheet, that's the fabric of the cosmos. Put a heavy object in the center, a bowling ball. The sheet stretches, it sags, creating a well around the weight. That's mass warping spacetime. Now roll a marble across that sheet. The marble won't go straight, it'll curve inward toward the bowling ball. It's not being pulled by a force, it's following the curvature, the groove carved by the heavy object. That marble is a planet, that bowling ball is the sun. Our solar system is a dance along these invisible contours. The math behind this is called the Einstein field equations. 10 interwoven equations. They describe how energy and mass dictate the curvature of spacetime, and how that curvature dictates how everything moves. It's a conversation. Matter tells spacetime how to curve. Spacetime tells matter how to move. That shift in perspective solved old mysteries. It explained the wobble in Mercury's orbit. And it made a prediction that light from distant stars would bend passing near the sun. During a solar eclipse in 1919, astronomers confirmed it. Starlight was deflected. The path of light curved by the sun's gravitational well, proving spacetime was flexible. Kip Thorne talks about the predictive power of this view. He says the equations contained seeds of phenomena so strange they seemed like fiction. They predicted regions of spacetime curved so severely nothing could escape. Black holes. For decades they were mathematical curiosities, ghosts in the equations. Until we began to find them. The same equations predicted colossal events like two black holes colliding would send ripples through spacetime, gravitational waves. It took a century, but in 2015 we detected them, a whisper from a billion light years away, confirming Einstein's blueprint. This geometric view does more than explain orbits. It redefines causality. It merges space and time into one dynamic entity, where you are and when you are become part of the same fabric. A massive object doesn't just bend the path through space. It bends the flow of time. Clocks tick slower in stronger gravity. That's not a metaphor. It's measured daily by GPS satellites. To pinpoint your location, those satellites have to account for time running faster for them, orbiting above, than for you on the surface. Without that correction, your map app would be off by miles in minutes. So Earth's orbit, it's not being whipped around on a string. It's rolling along a groove. A groove etched into reality by the sun's mass. That elegant distortion is our first and most tested map, the foundation. It tells us the stage isn't rigid. It's dynamic, and if the stage can bend and ripple, what other secrets might its architecture hold? But spacetime is this smooth, bending fabric until you look closer. Much closer, down at the smallest scales, there, Einstein's geometry starts to dissolve. It shimmers, it churns, it becomes a quantum foam, a sea of pure potential. That's the second blueprint, quantum field theory, and it gives us a reality so strange it redefines empty space. It's not a quiet stage, zoom in, and the vacuum is anything but empty. What we call nothing is a seething, turbulent ocean. The building blocks aren't solid balls, they're fields, invisible fields that fill all of space. There's an electromagnetic field, an electron field, a quark field, for every particle a corresponding field stretching across the cosmos, so an electron isn't a speck of dust. It's a localized ripple, a tiny vibration in the universal electron field. A particle is just an excitation of its field, a note played on an invisible instrument. And the vacuum, the lowest energy state, isn't silent. It has a constant, faint hum. These fields are never perfectly still. They jitter, they fluctuate. That quantum jitter allows something bizarre. Pairs of virtual particles, a particle and its antimatter twin, can pop into existence. They borrow energy from the vacuum, then annihilate and vanish a moment later. This isn't speculation. We see its effects in lab measurements. The vacuum, as Frank Wilczek said, is a lively place. All this frantic activity should contain an enormous amount of energy. Vacuum energy, and it creates one of the biggest puzzles in physics, the cosmological constant problem. When physicists calculate how much energy this quantum foam should have, based on known fields and particles, the number is absurdly large. It should have over 100 zeros after it. That much energy woven into space would produce a repulsive force so powerful it would have ripped the universe apart instantly, long before any stars or galaxies could form. Yet, when astronomers look out, they measure the actual effect. It's incredibly small, almost zero, but not quite. It's the gentle push we call dark energy, accelerating the universe's expansion. The difference between the theoretical prediction and the observed reality is the largest mismatch in the history of science. It's like calculating that a single grain of sand should weigh as much as an entire galaxy. The numbers are that wrong. This isn't a small error. It's a screaming clue that something fundamental is missing. Our two most successful theories, the smooth geometry of general relativity for the large and the frothy chaos of quantum field theory for the small, are describing the same stage in two completely different languages. And they're telling two wildly different stories about its most basic property. This tension isn't a flaw, it's a beacon, pointing toward a deeper, unified layer of reality waiting beneath the quantum foam. Those two stories, the smooth curve and the quantum foam, they can't both be the final answer. They have to be different melodies from the same instrument. So there's a third blueprint, string theory. It starts with a simple idea. What if the most basic things aren't zero-dimensional points? What if they're one-dimensional strings? Vibrating, think of a violin string. Pluck it one way, you get one note. Pluck it another, you get a different note. In string theory, every particle is a different note. An electron is one vibration of a string, a quark is another, the photon, that's another, even the graviton, the particle for gravity, it's just a distinct vibration. So in one move, this unifies everything, all forces, all matter. They're just different resonances on the same tiny loops. Brian Greene described it as a cosmic symphony, played on strings that are 100 billion times smaller than an atomic nucleus. But for that symphony to work, the strings need more room. More room to vibrate than our 3 dimensions of space. The math demands extra dimensions, not 1 or 2, 6 or 7 more spatial dimensions, all curled up into these incredibly complex shapes, Calabi-Yau manifolds. It's like a garden hose. From far away, it looks like a line, one-dimensional, but up close, you see it has a second dimension. A small circle curled around its length. The extra dimensions in string theory are like that, but far more intricate. a Calabi-Yau shape is a six-dimensional object. Folded and twisted upon itself at every point in our familiar space, and each distinct way to fold those dimensions, it could produce a different set of notes. A different universe with different particles, different forces, which leads to a staggering possibility. Our universe with its specific laws might just be one possibility. One in an almost infinite landscape of possible universes. The hope was this single framework would finally weave quantum mechanics and gravity together. One seamless tapestry, spacetime itself would emerge from the collective behavior of strings. But for all its mathematical beauty, string theory has a problem. The energy scales where strings vibrate are unimaginably high, far beyond any collider we could ever build. And with that vast landscape of possible solutions, it's been hard to make a unique prediction. A testable one for our specific universe, so we're left with this breathtaking vision, but for now, it's a magnificent speculation. Is the cosmos really built from vibrating strings? Are we just the harmonics of a hidden geometry? The theory offers a lesson that the search for unity might mean letting go of our basic intuition, that particles are little dots, and instead listening for a deeper music. And if the fabric is woven from strings, what happens when you stretch those strings to their absolute limit? That leads to a place where even strings might break down, a point of infinite density, a singularity. If strings are adding dimensions, maybe the stage itself is the problem. What if space isn't smooth? There's another blueprint. It doesn't add dimensions, it breaks them apart. Loop quantum gravity. It says spacetime isn't a continuous fabric. It's more like a tapestry woven from threads. The fabric has a grain, a pixelated structure. This is a quantum description of gravity. You start with Einstein's geometric view of spacetime. Then you apply quantum mechanics to it directly. The result is a universe made of tiny, discrete grains of space at the Planck scale, a scale so small it's 100 trillion times smaller than an atom. At that scale, smooth geometry breaks. It becomes a network, a web of interconnected loops. These loops are the quantized threads of the gravitational field. They form a spin network. Each link in that network carries a quantum number, a spin, and the pattern of the web, how those links connect, that defines the volume. The shape of space at that point. Space isn't a container, it's the network itself, a cloud of relationships. That's how Carlo Rovelli describes it. But if space is quantum, then time has to be quantum too. That's where spin foam comes in. Take that spin network, that frozen snapshot of space. Now imagine it changing, evolving. The history of those changes isn't a smooth movie. It's a sequence of still images, like a flipbook. The foam is the quantum history of spacetime, a bubbling structure. Each bubble is a quantum event. A pixel of spacetime coming into being. This leads to a profound point. It means there's a smallest possible unit of space, a quantum of volume, and a smallest possible unit of time. A tick of the cosmic clock. You can't divide space or time any further. This solves a major problem from Einstein's theory, the singularity. In general relativity, at the center of a black hole or at the Big Bang, the equations break. Density becomes infinite, curvature becomes infinite. That's a sign the theory is incomplete. But in loop quantum gravity, you can't have infinite density. Because you can't cram matter into a volume smaller than the smallest quantum of space. The granularity of spacetime acts like a cushion. It stops the collapse into a true mathematical infinity. So the Big Bang might not have been a singular beginning from nothing. It could have been a big bounce, a prior universe contracting to a dense state, then rebounding into our expansion. The singularity is replaced by a quantum transition, a cosmic reboot. This blueprint has a different aesthetic, no extra dimensions, no vibrating strings. Just a universe built from the relationships between events, a dynamic, pixelated entity, geometry born from connection. It asks us to let go of continuity, to see the world not as a flowing river, but as the individual frames of a film. If space is a network and time is a sequence of changes in that network, then what we experience as the smooth flow of reality is an illusion. An emergent picture, like the smoothness of a television image coming from millions of tiny pixels. So which is it? A symphony of strings in hidden dimensions, or a cosmic network of quantum links? The search for the true blueprint continues, and the next contender comes from a place that sounds like science fiction, a universe that isn't fundamentally real but a projection. A cosmic hologram, but space and time as a network of quantum links that raises a question. What's doing the connecting? What is the link itself? There's a fifth blueprint. It takes that idea to an ultimate, minimalist end, causal set theory. It says the most fundamental thing about reality isn't space, it isn't even time. It's causality, the simple, unbreakable relationship of cause and effect. At the bedrock, there's just a vast collection of discrete events. Think of them as the most basic moments. Indivisible ticks of a cosmic clock. These events aren't placed in some pre-existing space or time. The only thing that defines them is their order, a single, powerful relationship. This event can influence that one. That's the causal connection. One event is in the past of another. Our whole smooth, four-dimensional universe, the distances, the durations, that's an illusion. It emerges from this colossal web of cause and effect. As physicist Raphael Sorkin put it, order plus number equals geometry. The order is the causal relationship between events. The number is just how many events there are. From these two sparse ingredients, a list of points, and a list of which points precede others, the full richness of spacetime geometry is supposed to materialize. It's a staggering shift. We don't live in a container. We live within a pattern of relationships. This approach solves some deep problems with elegant simplicity. For one, it naturally includes an arrow of time. In our everyday experience, time has a direction. We remember the past, we anticipate the future. In most physical theories, the fundamental equations are symmetric. They work just as well running backwards, but in a causal set, the relationship is inherently one way. If event A can influence event B, then B cannot influence A. The fundamental structure has a built-in directionality. The flow of time we experience could emerge from that. It also avoids the infinities that plague other theories. In Einstein's equations, singularities are points where quantities like density become infinite. That's a sign the math has broken down, but in a causal set, there's no continuum to become infinitely curved. Reality is granular. There's a finite number of events in any finite volume of space-time. You simply cannot pack an infinite number of causes into a finite region. The theory imposes a kind of cosmic speed limit on how much stuff can happen anywhere. So what would this universe look like at its core? Imagine the most sparse, abstract sketch of history possible. Not a timeline, a vast, growing graph. Each dot is a fundamental event. A line connects two dots only if one can affect the other. From this seemingly chaotic, unordered-looking graph, the smooth, orderly spacetime of stars and planets must somehow arise. It suggests the distance between two stars, the time it takes light to travel between them. That's not a primary property. It's a secondary calculation. A consequence of counting how many causal events lie on the shortest possible chain of influence connecting them. The fabric isn't woven, it is counted. This is perhaps the most austere vision of them all. It strips reality down to its barest logical bones. Before geometry, before matter, there was only connection. A cosmic story written not in places but in possibilities. And if the stage is just a story of cause and effect, what does that say about the actors upon it? That leads to a blueprint that places information itself as the primary substance of reality. light isn't just moving through space, it might be what space is made of. That's the idea in twistor theory. You stop thinking about points, about positions. You think about the paths of light rays. A twistor is the math for a light ray in flight. It holds where it is, its momentum, its direction. Roger Penrose started this. The basic things aren't objects in a location. They're these luminous threads that connect events. Our normal spacetime, the four-dimensional grid that becomes something secondary, it comes out of a deeper geometry, a twistor space. In that space, the equations of physics get simpler. How particles interact and scatter, problems that are huge in the old way can sometimes be solved in a few lines. It's not just a neat trick, it means we've been looking from the wrong angle. We see objects inside a container. Twistor theory says the container is built from the relationships, from these light-like connections, and it fits with something strange in quantum mechanics. Non-locality, two entangled particles affecting each other instantly, no matter the distance, as if the space between them isn't really there. In the twistor view, that starts to make sense. If spacetime points come from a network of light rays, then what looks like a vast separation might be a direct link in the underlying space. The distance is an illusion. It's how we've built our perspective, and that leads to another idea, the holographic principle. We'll get to that soon, but the link is important. The holographic principle says all the information in a volume can be encoded on its boundary. Twistor theory gives a natural math for that. The complex geometry of twistor space can project a lower dimensional description, like a hologram projecting a 3D image from a 2D surface. Penrose has thought that twistor elements might be more primitive than spacetime itself. Our intuition about locality, that things only affect nearby things, might just be a useful approximation. Not a fundamental law. The cosmos isn't a collection of places, it's a tapestry of connections, a web of luminous links. In this picture, a particle, an electron, isn't a tiny ball at a point. It's more like a knot, a stable twist in this network of light-like relationships. Reality is woven from causality and connection. Light is the thread. So when you look at the night sky, you're not just seeing distant points of light in a void. You're seeing the threads of the cosmic fabric stretched across the eons. Showing the architecture of everything, twistors suggest something deeper, that what we see might be a projection, and that brings us to the seventh blueprint. The holographic principle. It starts with a problem about black holes. In general relativity, a black hole has an event horizon, a point of no return. And the information about what fell in the specific details seems to be lost, gone forever inside. But quantum mechanics has a rule: information can't be destroyed. It can get scrambled but never erased. That was Stephen Hawking's puzzle, the black hole information paradox. Leonard Susskind and Gerard Hooft had a radical idea. Maybe the information isn't lost inside, maybe it never actually falls in. Instead, it gets perfectly encoded, painted right onto the event horizon itself. The two-dimensional surface of the black hole, all the data about the star, the dust, the spacecraft, it's all stored there on the skin, like an incredibly dense cosmic film. The three-dimensional interior, the volume we picture, becomes a kind of illusion, a projection from that two-dimensional data, like a hologram. A security hologram on a credit card is a flat, patterned surface. But light hits it and it projects a three-dimensional image. The holographic principle says our universe might work that way. We live in the three-dimensional projection. But the true reality, the master copy, exists on a distant two-dimensional surface at the boundary of space, and this isn't just about black holes. It's about all of space. The principle says all the information in any volume of space can be encoded on its surrounding surface. Think of your living room. Every object, every dust mote, the air itself. In theory, you could capture all the data to reconstruct it perfectly. not with cameras inside, but by writing a description on the walls. The walls, a two-dimensional surface, hold the complete blueprint for the three-dimensional space they enclose. This reduces what's real. The true degrees of freedom, the fundamental building blocks, are vastly fewer. They don't fill the volume, they live on the skin. Gerard T. Hooft argued this means spacetime and gravity aren't fundamental. They're emergent, they come from something more basic. Quantum information, and how is that information connected? Through quantum entanglement, those spooky links between particles. The fabric of space itself might be woven from these threads of entanglement. Cut the entanglement and space itself might dissolve. So what are we in this picture? We are the illusion, sophisticated patterns in a grand projection. Our bodies, this planet, the distant galaxies, all a dynamic hologram, painted on the cosmological horizon, the ultimate boundary of the observable universe. It's a breathtaking idea, almost unsettling, that the solidity of the world, the very distance between stars, is a computed reality. A cosmic sleight of hand performed by information on a screen we cannot see. If reality is a hologram, then who or what is running the projection? The holographic principle describes reality as a projection, but you have to ask what's doing the projecting. What creates the sense of depth? The answer might be the strangest link in physics. Quantum entanglement, that's the eighth blueprint. These invisible threads could be stitching the cosmic fabric together. It starts with a simple experiment that's hard to believe. Take two particles and link them. Send them to opposite ends of the galaxy. Measure one, and the other instantly matches its state. This isn't a signal, it's a correlation that acts like space isn't even there. Einstein called it spooky action at a distance. He thought it showed a flaw. But tests have shown it's real. This spookiness might not be a mistake. It might be how things are built. The connection between entangled particles seems to go beyond space. So maybe it doesn't travel through space. Maybe it defines the space. Recent theory has given this idea a shape. It's called the ER equals EPR conjecture. Proposed by physicists like Maldacena and Susskind, it connects two different ideas. ER, that's Einstein-Rosen bridges, wormholes, theoretical tunnels. And EPR, that's the Einstein-Podolsky-Rosen paper, the one that pointed out the entanglement paradox. The conjecture says they're the same thing. Two entangled particles aren't talking across emptiness. They're linked by a microscopic wormhole, a tiny bridge in spacetime's geometry. In this view, entanglement isn't something happening in space, it's the architecture of space. More entanglement between two regions means a stronger geometric link. The fabric is woven from these quantum correlations. This gets a precise math form in something called entanglement entropy. It measures how entangled a system is. For a region of space, this entropy isn't proportional to the volume inside. It's proportional to the area of its boundary. That's a direct echo of the holographic principle. The information scales with the surface area. Maldacena's work shows this geometric area is counting the entangled threads crossing that boundary. So space emerges from a vast network of quantum links. Think of a tapestry. From far away, it's a smooth image. Up close, it's countless individual threads. The threads are the entanglements. The smooth image is the space-time we experience. This implies something deep. Without entanglement, the continuum might not exist. There'd be no here and there, no distance. The universe would be a disconnected swarm of possibilities. Entanglement is the quantum glue that creates the stage. So when you feel the ground under your feet, or look at the vast distance to a star, you're not seeing a fundamental emptiness. You're seeing the pattern of an unimaginably complex web. A web of invisible threads tying everything together. And if entanglement builds the stage, what about the actors? It suggests our existence as separate, localized beings is also part of the illusion. We are knots in the net, which leads to a blueprint that asks the ultimate question about that net. Is it just a random pattern, or is it a computation? Is the universe itself a cosmic computer? Gravity might not be a force. It could be a side effect, an illusion. The ninth blueprint pushes the holographic idea as far as it can go. It asks if gravity emerges from something more basic, like temperature. You don't feel temperature as a fundamental thing. It's a collective effect, a statistical average of all these tiny atomic motions. So emergent gravity says gravity works that way too. It's an entropic force, a push toward disorder. Physicist Eric Verland had this idea. He starts with a holographic screen. That boundary where information is stored. Now picture a particle moving toward that screen. As it gets closer, it changes the information on the screen. The entropy there, the disorder, increases, and nature always tends toward maximum entropy, so the system rearranges itself. It accommodates that new information. That rearrangement, that drive to maximize disorder, shows up as an attractive force. We call that gravity. It's not a pull, it's a statistical nudge. A nudge toward a more likely configuration. Think of a crowd in a room. If you walk through, people shift to make space. You feel a pressure, a resistance. But no single person is pushing you. The collective movement of the crowd creates that effect. Gravity, in this view, is the crowd. Space-time geometry isn't the stage. It's more like the surface of a fluid. Watch a whirlpool form in draining water. The vortex isn't a fundamental object, it's a pattern. It emerges from countless water molecules interacting. From pressure and flow, the smooth curve of spacetime in Einstein's theory would be like that vortex, a large-scale description of something far more microscopic. This directly challenges general relativity. Einstein saw geometry as primary. Matter tells spacetime how to curve. But here, geometry is secondary. It's a thermodynamic gradient. A slope in an information-theoretic landscape. What we perceive as curvature guiding planets is actually a slope in information density. It's a staggering shift. It means the force that holds galaxies together, that keeps your feet on the ground, is a kind of statistical mirage, a consequence of the universe's relentless drive toward disorder. So the next time you drop something, watch it fall. That acceleration isn't a tug from the Earth's mass. It's the universe efficiently managing its information, nudging everything toward a state of higher entropy. If gravity is an emergent illusion, what else about our cosmic stage might be just a useful story? This leads to a blueprint that questions the stories we tell. The narratives of cause and effect that shape our reality. That cosmic computer, that emergent gravity, it all needs a stage with a definite structure. But the stage itself might be uncertain. The 10th blueprint introduces a space where measurement blurs the map, non-commutative geometry. In our world, order usually doesn't matter. Drive 5 miles north, then 5 miles east, or east, then north. You end up in the same spot. The operations commute. In the quantum world, this breaks. Measuring a particle's position, then its momentum, gives a different result than measuring its momentum, then its position. The order changes the outcome. They do not commute. Alain Connes asked a question. What if spacetime coordinates have this quantum property? What if pinpointing here and now precisely is impossible? Not because of our instruments, but because the concept itself is fuzzy. In this geometry, the coordinates aren't simple numbers, they're mathematical operators, and because they don't commute, you can't specify all of them with infinite precision at once. There's a built-in uncertainty woven into the fabric. This isn't a small correction. It generalizes our idea of space. The smooth, continuous stage of classical physics is a special case. A quiet, low-energy approximation. The true geometry is more rich. It can describe spaces that are inherently granular, or spaces with extra, hidden dimensions. Not dimensions of size, but of a more abstract, algebraic nature. This framework has a power. it can naturally incorporate the entire standard model of particle physics, the quarks, leptons, and forces, as geometric features. In this view, the Higgs boson, the particle that gives others mass, isn't an extra thing added to spacetime. It's a manifestation of the geometry's internal vibrations. The forces we see are the curvature of this new, non-commutative landscape. It suggests Einstein's equations for gravity might be just one part of a larger set. Equations that also describe the quantum particles dancing on that stage, all unified by a single geometric principle. The implication is that at the tiniest scales near the Planck length, the universe isn't just pixelated. It's probabilistic. The distance between two events isn't a fixed number. It exists within a range of possibilities. The ideas of here and there become statistical. Blurred, think of it like this. You're trying to draw a map of a city, but your pen is a quantum object. The more precisely you try to mark a street corner, the fuzzier the street name becomes. The map itself resists being pinned down. Reality at its foundation is not a sharp photograph. It is a watercolor painting with edges that bleed into one another. A canvas of inherent potential. So when we speak of the fabric of spacetime, we must now imagine a fabric that is not merely woven, but one that hums with a quantum uncertainty. Its threads are not static lines, but vibrations of probability. This blueprint doesn't just change our map of the cosmos. It changes the very nature of cartography. If the coordinates are fuzzy, what does that say about the events that happen within them? It suggests that history itself, the causal chain of the universe, might have a quantum texture. A fuzziness to its past. The fuzzy watercolor needs to dry. It has to become crisp. How does that happen? One answer is to build it, block by block. The 11th blueprint is causal dynamical triangulations. It builds reality from the simplest shapes, four-dimensional simplexes. They're the most basic building blocks, like Legos. You don't start with a smooth stage. You start with a vast collection of these identical blocks, and you glue their faces together, but not randomly. There's a strict rule, causality. Every block has an arrow of time. You can only connect them in ways that respect the flow, past to future. No time loops, no disconnected moments. You're assembling the history of a universe. One causal step at a time. This is a computer's dream. You can actually do this. You can program a simulation. Start with a soup of a few thousand simplexes. Let the rules run. Let the program sum over every possible way to glue them together. That approximates the path integral, the sum over all possible histories. And when you run it, something happens. From the chaotic microscopic soup, a large-scale, smooth universe crystallizes. It emerges by itself. The simulation doesn't produce a crumpled mess. It produces a world that looks like ours, 3 extended spatial dimensions, one of time. This was a profound result from physicists like Jan Amjorn. They found that imposing causality was the key, that simple rule of cause and effect. It acts like an organizer. It prevents pathological, crumpled universes. It guides the random gluing toward a stable, classical reality. So what are we seeing? We're watching spacetime knit itself together. Each simplex is a quantum event. A pixel of reality. The gluing rules are the quantum dynamics. The large, smooth spacetime is the collective behavior. It's like a mosaic. Up close, you see the individual, jagged tiles. Step back and a smooth picture appears. The distance between stars, the flow of time. These aren't input, they're the output. They're measurements you make on the connected web of blocks after it has grown. This blueprint is tangible. It doesn't require hidden dimensions or vibrating strings. It says the fabric might be a combinatoric structure, a cosmic tapestry woven from a finite set of rules. The smooth continuum of Einstein is an illusion of scale, a statistical reality that emerges when you have an astronomical number of quantum tiles. So our universe may not be a pre-written script. It may be a story being assembled, one causal moment at a time, a story whose plot is written by the simple logic of connection. But if the universe is assembling itself from blocks, what is it assembling toward? What's the shape of the final picture? That question leads to a blueprint that doesn't build from the bottom up, it constrains from the top down, the universe putting itself together from blocks. That makes you wonder what guides it. Maybe there's a blueprint that doesn't need new parts, just finds a perfect balance in the old ones. The 12th blueprint is asymptotic safety. It's a radical simplicity. Maybe quantum gravity isn't broken. Maybe we just haven't solved it right. The core problem is infinity. In ordinary quantum field theory, when you calculate things like particle collisions, you often get infinite answers. Nonsense answers. Physicists use a trick called renormalization to sweep those infinities under the rug. It works for the electromagnetic force, the nuclear forces. But for gravity, the trick fails. The infinities pile up, they're uncontrollable. Asymptotic safety asks if we're looking at it wrong. What if gravity, at its quantum heart, doesn't produce those infinities at all? The key is the renormalization group flow. Think of it as looking through a series of lenses. A low-energy lens, you see planets, people, smooth spacetime. Zoom in with a higher energy lens, you see atoms, particles, quantum foam. Each lens, each energy scale has its own effective description, its own set of rules and numbers. The renormalization group describes how those rules change as you zoom. Usually, the numbers drift. The coupling constants change with the energy scale. For gravity, this drift seems to lead to a mess, but in the asymptotic safety scenario from the work of Martin Reuter, there's a special point, a fixed point. Imagine a marble rolling on a complex, multi-dimensional landscape. Most paths lead the marble off into infinity. That's the usual, problematic drift. But there is one path, a ridgeline, that leads to a basin, a stable point where the marble comes to rest. In this metaphor, the marble's position is the strength of gravity's coupling. The basin is the fixed point. If the theory's parameters lie on that special path, they flow toward that fixed point as you zoom to higher energies, all the way to the Planck scale. At that point, the theory becomes scale invariant. It looks the same at all magnifications, and it yields finite, sensible answers, no infinities. In this picture, gravity is a perfectly well-behaved quantum field theory. It just has this special, asymptotically safe trajectory. The fabric of spacetime doesn't need to be replaced by strings or pixels. It can remain a continuum. But a continuum with a secret. At extremely high energies near the fixed point, spacetime is predicted to develop fractal-like properties. Its effective dimension shrinks. From our familiar 4 dimensions, it might flow down to 2. Space becomes wildly wrinkled, folded in on itself at the smallest scales, yet never tearing into discrete pieces. It's a mesmerizing vision, a universe where the stage is both continuous and quantum all at once. It offers a bridge, a way to keep the language of fields and particles we know, and simply extend it to include gravity by finding its hidden, safe harbor. This blueprint doesn't invent a new reality. It suggests we just need a better map of the old one, a map that reveals the stable path through the landscape of all possible theories. If the fabric can be both continuous and safe, what other symmetries might be hiding within its weave? That stable path through the landscape leads to a startling possibility. Maybe our universe isn't the only possible configuration. It might just be one room in an infinite mansion. The 13th blueprint is the multiverse's tapestry of bubbles. Our entire cosmos, with all its galaxies and forces, could be a single bubble, floating in a frothing, eternal sea of other bubbles, each with its own rules. This vision comes from 2 powerful ideas coming together. The first is cosmic inflation, the theory that in the first fraction of a second, space itself expanded faster than light. stretching a quantum speck into a macroscopic universe. But what if inflation doesn't have a single, neat endpoint? What if, in some regions, it stops and a stable bubble universe like ours forms? But in other regions, the inflationary energy field persists. It keeps expanding eternally, and within that eternally inflating background, new bubbles are constantly popping into existence. Nucleating like bubbles forming in a pot of boiling water that never stops boiling. This is eternal inflation. The second idea comes from string theory's landscape. Those Calabi-Yau shapes, the curled-up extra dimensions, the theory suggests there are a staggering number of ways to fold them, perhaps 10 to the 500 different stable configurations. Each configuration corresponds to a different set of physical laws, different particle masses, different strengths for the forces, even a different number of extended spatial dimensions. In this vast landscape, our universe, with its specific constants that allow for stars and planets and life, is just one possibility, one entry in a cosmic catalogue of unimaginable size. André Linde helped paint this picture. He described a meta-universe, a multiverse, where inflation is the default, eternal state. Our bubble is a local fluctuation where the inflationary field decayed. It gave birth to the hot Big Bang we trace our history to, but beyond our bubble wall, the inflation continues, giving birth to an endless number of other pocket universes. Some might have stronger gravity, collapsing instantly. Others might have no atoms, just a featureless soup. Some might have 5 large dimensions. Their physics would be utterly alien. In this view, the fundamental constants aren't fine-tuned by a designer. They are environmental. They are local bylaws, the result of a random roll of the dice in our particular pocket of the multiverse. This reshapes the very question of why our universe is the way it is. We don't ask why the air pressure is what it is on Earth. It's a local condition on our planet. The multiverse theory suggests the laws of physics might be similar, a local condition in our cosmic neighborhood. The fabric isn't singular, it's a quilt. A patchwork of disparate realms stitched together by the frenetic process of eternal inflation. We are living on one patch, unable to see the others because light cannot travel faster than the inflating space between the bubbles. The walls of our pocket universe are our ultimate cosmological horizon. It challenges a deep-seated assumption that our local physics defines a universal blueprint for all of existence. It may not. Our blueprint might be a regional building code, one of countless codes across an infinite construction site. This idea is humbling and expansive. It turns the quest for a single theory of everything into a cosmic census, an attempt to understand not just our home, but the nature of the entire neighborhood. And if our universe is a bubble among bubbles, what determines its initial shape, its first moment? That question pulls us toward a blueprint with no beginning at all. A bubble universe has a beginning, but the idea of a beginning might be an illusion. The 14th blueprint is a radical shift. It's called shape dynamics. It's a relational revolution. The geometry of space isn't an absolute stage that exists beforehand. It's defined by the relationships between the objects inside it. There's no background container. There's only the configuration of things, their relative distances, their angles, their shapes. This is a reformulation of Einstein's theory, but with a twist. In general relativity, the fabric has a metric, a ruler that measures absolute distances and durations. Shape dynamics says scale itself is redundant. It's a gauge, a convention. If you doubled the size of the entire universe instantly, every ruler, every atom, every wavelength of light would stretch in proportion. Nothing would change, no experiment could detect it, so why treat size as fundamental? Instead, shape dynamics focuses only on shapes, the angles between galaxies. The ratios of distances, the pure configuration of the cosmos. In this view, time doesn't flow as a separate river. it emerges from change in these configurations. One now is a single, frozen shape of the entire universe, a snapshot of all the relationships between everything. The next now is a different shape, a slightly altered arrangement. What we experience as the passage of time is just our consciousness moving through this succession of nows. This timeless perspective was championed by Julian Barber. He suggests the universe isn't a movie playing out on a screen of spacetime. It's a vast stack of still photographs. Each photograph is complete and real. Our feeling of motion, of history, is our path through the gallery. This solves a problem in quantum gravity, the problem of time. In many approaches, when you apply quantum rules to the whole universe, the time variable drops out. The equations become timeless. Shape dynamics embraces this. It says time isn't a fundamental ingredient in the recipe. It's a flavor that arises when you taste the cake. The fundamental reality is a landscape of possible shapes, and our history is a winding path through that landscape. So what weaves the fabric then? It's not a metric, not a grid of coordinates. It's the relational structure itself, the network of betweens. Think of a mobile hanging from a ceiling. The artwork isn't the empty air around it. The artwork is the set of distances and angles between the dangling pieces. Twist one piece and the entire configuration changes. The relationships redefine the whole. Our universe is that mobile. The planets, stars, and galaxies are the pieces. The fabric is the ever-shifting pattern of their connections. This asks us to reconsider everything. The distance to the Sun isn't an absolute 93 million miles. It's a relationship between the Earth and the Sun, defined in the context of all other relationships in the cosmos. The stage isn't set before the dancers arrive. The dancers, through their relative positions and movements, conjure the stage into being with every step. Space-time is not a container, it's a record. A living ledger of evolving relationships, a cosmic dance where the dancers define the floor beneath their feet. If the fabric is pure relationship, what is the substance that is relating? This leads to a blueprint that makes that substance as minimal as possible. Pure information flashing into existence one bit at a time. The cosmic dance needs a medium, something for the connections to be in. The 15th blueprint has a candidate, and it's something we know. Matter, the gravity model says space-time is a phase of matter, not matter in space, space as matter, a frozen network of quantum links, so you picture the first moment. Not a point of infinite density, but a state of maximum connection, a seething, abstract graph. Imagine a vast crowd, every person holding hands with every other person. That's the primordial state. Each person is a fundamental node, a quantum bit of existence. Each handshake is a quantum link, an entanglement. The whole system is a featureless soup. A high-dimensional soup of pure potential. No here or there, no before or after, just total connectivity. Then something happens. The universe cools. In physics, when a liquid cools, its molecules lose energy. They settle into a regular crystalline structure. Water becomes ice. The gravity model suggests something analogous happened to reality. As the quantum graph lost energy, it underwent a phase transition. It froze, but it didn't freeze into a random tangle. It froze into a specific, low-dimensional lattice. A crystalline structure for spacetime itself. In this frozen graph, most of the original handshakes are broken. Each node is now only connected to a handful of its nearest neighbors. This sparse, regular connectivity creates the illusion of dimensionality. In a perfect grid where each node connects to 4 others, the large-scale structure looks 2-dimensional. Connect to 6 neighbors and it mimics 3 dimensions. The model's name, graphity, comes from this graph plus gravity. The geometry of gravity emerges from the graph's connectivity. This is a powerful shift. Lorentz invariance, the principle that physics is the same for all observers moving at constant velocity. isn't a fundamental postulate. It's an emergent symmetry. It arises because on average and at large scales, the frozen graph looks the same in all directions. It has translational and rotational symmetry. Like the atomic lattice in a crystal looks smooth and uniform from a distance, even more, the model suggests particles could be excitations of this graph. Flaws in the lattice or collective vibrations traveling through it, like sound waves in a crystal. The entire zoo of particles and forces could, in principle, be different vibrational modes of this single quantum network. So the smooth, continuous stage of relativity is an approximation, a very good one, like describing a diamond as a smooth, hard object, but up close, a diamond has a rigid atomic lattice. Up close, spacetime has a graph-like structure. We don't perceive the individual nodes and links because we are made of them. Our perception is calibrated to the large-scale, frozen phase. We are like fish who have never known anything but water, unaware the medium they swim in has a discrete molecular nature. This blueprint gives a tangible metaphor. Space is not a passive backdrop. It is a dynamic substance that can change state. It had a history, it cooled, it crystallized, and the laws of physics we measure today are the local bylaws of this cosmic crystal. What if somewhere the graph froze differently? The result would be a universe with a different number of dimensions, or with physics utterly alien to our own. The fabric isn't merely woven, it is grown and frozen into the shape we call home. That cosmic crystal didn't freeze all at once. It has a pulse. The 16th blueprint is called quantum graphity. It takes that frozen graph and breathes quantum life back into it. The links aren't permanent. They can turn on and off, so the network is dynamic, a living lattice. In this view, the early universe wasn't a point. It was a state of maximum connection. Every fundamental node was linked to every other. Imagine a room where every person is shaking hands with everyone else at the same time. It's a chaotic, buzzing web, no sense of direction or distance, a high-dimensional soup. That's the hot, dense beginning. Then expansion happens, cooling. As the universe cools, maintaining all those links becomes costly, energetically costly. Links begin to break. It's a cosmic game of musical chairs. As the music of creation slows, the nodes settle. They settle into a stable, sparse pattern of connections. Most handshakes are released. Each node ends up linked only to a few nearest neighbors. That sparse, regular pattern is what we perceive as three-dimensional space. The dimensionality isn't built in. It emerges from the connectivity. A grid where each node connects to 6 others will, on a large scale, behave like a three-dimensional continuum. Our familiar space crystallized out of that cooling quantum graph, but the process didn't end there. The broken links left behind traces, defects in the crystalline structure. Think of water freezing into ice. Sometimes air bubbles get trapped, or the ice forms with tiny cracks, imperfections. In the freezing spacetime graph, similar defects could have formed. Fotini Markopoulou and others have suggested these defects aren't flaws. They are the seeds of particles. A trapped defect in the network's geometry could behave like an electron. A vibrating string of broken links could act like a photon. The gauge forces we know, electromagnetism, the nuclear forces, they might arise from conserved quantities. From how the network dynamically rewires itself. In this blueprint, the speed of light isn't a fundamental constant of a vacuum. It's an emergent property. The maximum speed at which a change in connectivity can propagate across the network. A broken link turning on or a defect moving. The fabric's frozen geometry sets that universal speed limit. This paints a picture, a stunning picture of cosmic history. Space-time isn't a static stage upon which the drama of particles unfolds. It is the drama. The stage and the actors are made of the same substance. The universe began as a formless, interconnected whole. Through a grand phase transition, it crystallized into the structured reality we inhabit. The constants of nature are not arbitrary numbers, they are frozen echoes of that transition, the specific way our particular graph cooled and locked into place. This is a universe that built its own container from the inside out, and if the links are still dynamic, still capable of change at some level, it suggests the fabric might still be evolving. Imperceptibly slowly, the crystal of reality might have a subtle quantum flexibility, a memory of its hot, connected birth. That cosmic crystal, this network of dynamic links, it points to a deeper unity. The actors and the stage might be the same thing. The 17th blueprint makes that explicit. It's called causal fermion systems. Here, the fundamental substance of reality isn't a particle. It isn't a field or a graph, it's a sea of possibilities, a mathematical ensemble. Each element in that sea is a fermionic wave function, a quantum possibility for matter. But these wave functions, they don't live in a pre-existing space. They define space through their interactions, their causal relationships. The architect of this, Felix Finster, starts with a simple shift. He asks, what if we describe the universe not by what is where, but by what can influence what? The basic objects are these fermionic wave functions. And the only rule is causality. One wave function can influence another, that's it. From this sparse starting point, a collection of things that can affect each other, the entire tapestry of physics is meant to emerge. The magic is in the correlations. When you have a vast number of these interacting possibilities, patterns form, statistical patterns. These patterns, these correlations between the wave functions, they create the illusion of a continuous background. They generate what we measure as the metric of spacetime. The curvature from Einstein's equations arises naturally from the collective behavior of this fermionic ensemble. In a similar way, all the particles and forces, the quarks, electrons, photons, they're not things put into the universe. They are excitations, ripples and structures within this single, unified substance. Think of it like the surface of a pond. From far away, you see a smooth, continuous sheet of water. That's spacetime, but up close, you see the water is made of countless molecules. The molecules aren't in the water, they are the water. Now imagine the reflections on the surface, the sunlight and the shadows, those aren't separate either. They are also patterns formed by the arrangement and motion of the very same water molecules. In this blueprint, the water is the causal fermion system. The smooth surface is emergent spacetime. The light and shadows are the emergent particles and forces. It is all one substance expressing itself in different ways. This framework doesn't quantize gravity as an afterthought. It doesn't start with a spacetime and then try to make it quantum. It starts with a quantum causal structure and derives spacetime. Gravity and the other forces appear on equal footing, as different aspects of the same underlying correlations. The theory naturally includes quantum mechanics because its fundamental objects are quantum wave functions. And it includes general relativity because the collective dynamics of those wave functions produces a geometric description at large scales. It presents a cosmos of stunning economy. There is no separate stage and no separate actors. There is only the ensemble. The fabric is not a backdrop. It is the intricate, dynamic pattern woven from the threads of existence themselves. Every star, every planet, every one of us is a complex, stable pattern within this fundamental sea. We are not inhabitants of the universe. We are vibrations of its single, unified substance. Condensations of a deeper reality that knows no distinction between the container and the contained. If all of reality is a single substance expressing itself, what dictates the form that expression takes? That leads to a blueprint that sees the universe not as a thing but as a process of constant creation. That unified substance isn't confined to one timeline. It could be negotiating its existence across all of time at once. The 18th blueprint is the transactional interpretation. It gives a radical answer to quantum weirdness. In this view, a particle isn't just a wave of possibility moving forward. It's also an echo from the future, calling it into being. John Cramer proposed this. Every quantum event is settled by a transaction, a handshake across time. It starts with an emitter, an atom, a star, any source. It sends out an offer wave. That's a retarded wave. It moves forward in time like waves normally do. It spreads out, exploring all possible paths. It reaches potential receivers. But that's only half. Each possible receiver in response sends back a confirmation wave. That's an advanced wave. It moves backward in time from the future to the past. It travels the same path the offer wave took. When the advanced wave from a specific future meets the original offer wave at the source, they reinforce each other. They form a standing wave, a closed loop in time. That loop is the transaction, and that transaction is what we observe as a real, definite event. The particle went from here to there. The cat is alive. The electron went through the left slit. The universe chooses one concrete history from a fog of possibilities through this negotiation. Think of it like a business deal. The source sends a proposal, a bid. Various futures send back acceptances. Only when a bid and an acceptance match perfectly does a contract get signed. The signed contract is the real event. The fabric of spacetime, then, is woven from an unimaginably dense web of these closed loops. Each transaction is a stitch, linking a point in the past to a point in the future. The smooth geometry we perceive is the large-scale pattern of countless completed handshakes. This gives a startlingly physical mechanism for something like quantum non-locality. Two entangled particles aren't magically communicating faster than light. Their transaction was a single, timeless loop established at their creation. The measurement just reveals which loop was completed. It also offers a fresh view of causality. Cause and effect aren't a one-way street. The effect from the future helps select the cause from the past. The present moment becomes a nexus, a dense intersection of transactions that have been settled and transactions being proposed. We are living in the crossfire of waves from the past and waves from the future. Our reality is the standing pattern they create. This implies a participatory universe in the most literal sense. The geometry of spacetime isn't preset. It is written, it is authored by these countless quantum handshakes. Every emission, every absorption, every observation is part of the authorship. The flow of time we feel may be our consciousness moving through this ever-thickening web of completed transactions. We are not passive travelers on a river of time. We are active participants in a cosmic negotiation where the future is just as involved in shaping the present as the past. If the present is a negotiation, what is being negotiated? It suggests the very laws of physics, the constants we hold as fixed, might be the long-term treaties of this process. The stable outcomes of an eternal conversation across time. Negotiations across time suggest a process, and a process needs rules. The 19th blueprint offers a rulebook. It says the universe isn't just like a computer, it is one, the Wolfram model. The cosmos is a computational process. It's breathtakingly simple. The fundamental stuff isn't matter or energy. It's abstract points and the connections between them, a hypergraph. A hypergraph is a generalization of a network. Its connections, called hyperedges, can link any number of points. Not just two. The universe starts as a simple hypergraph, maybe trivial, then a rule is applied, a single, deterministic rule for rewriting that graph. It might say, when you find a pattern of 3 points connected a certain way, replace it with a new pattern of 5 points, connected in a different way. This rule is applied over and over, everywhere it can be applied, in a vast, automated sequence. That's the cosmic computation. Each application of the rule is a discrete step. A tick of the cosmic clock. From this relentless, simple rewriting, everything emerges. all the richness of physics, all the complexity of our world. Stephen Wolfram suggests the laws of physics aren't fundamental. They're emergent regularities, stable patterns that arise from the underlying computational chaos. Like the laws of fluid dynamics emerge from the chaotic motion of countless molecules, so how does smooth, curved spacetime come from a discrete, churning hypergraph? It's in the connections. As the hypergraph evolves, the density of connections in a region isn't uniform. Some areas become more densely woven, others are more sparse. This variation in connection density is what we perceive as curvature, a region of the hypergraph that is highly connected, where points have many links, behaves like a region of highly curved spacetime. It acts like a gravitational well. A sparse region of the graph behaves like flat, empty space. Even dimensionality isn't a given. Our experience of three spatial dimensions could be an approximate, large-scale property of the hypergraph's connectivity. From the inside, as the graph grows and becomes incredibly complex, its large-scale statistical behavior might mimic a continuous three-dimensional manifold. We are inside the computation. We are patterns within the hypergraph. Our perception of continuous motion and smooth space is an illusion, generated because we are made of trillions upon trillions of these discrete rewriting events. Happening every moment, our consciousness samples this process at a rate too slow to see the individual steps. We see the movie, not the frames. In this digital physics blueprint, the Big Bang might be the first step of the computation. The initial hypergraph and the initial rule, the expansion of the universe is the hypergraph growing, becoming more complex, rewriting itself into existence. This is a universe of pure information, executing a single, elegant algorithm. The fabric is not woven, it is computed, one deterministic update at a time. It presents a cosmos that is both profoundly simple and infinitely complex. The ultimate source code for reality might be a few lines of logical instruction. And if that's true, then our search for the fundamental laws is not a search for equations of motion. It's a search for the ultimate program, the one rule to rule them all. That cosmic program rewrites reality step by step, but the steps themselves, the sequence, might be part of the illusion. The 20th blueprint shows a reality without time or space. The amplituhedron, it's a jewel of pure geometry, a shape in many dimensions, and its volume gives you the answer to one of physics' hardest questions: what happens when particles collide? For decades, physicists used Richard Feynman's diagrams for this. They're like little cartoons. Particles come in, they exchange virtual particles, they fly out. You have to sum over every possible diagram, every possible path, including strange loops where particles pop out of nothing and vanish. The math is monstrous. A jungle of infinities you have to carefully tame. But for certain theories, like one called n equals 4 super Young Mills, the amplituhedron changes everything. Developed by Nima Arkani-Hamed and others, this geometric object is a revelation. You don't sum over infinite paths through space and time. You don't even use space, time, or quantum fluctuations. Instead, you describe the incoming and outgoing particles with a set of abstract variables. These variables define the vertices of a shape, the amplituhedron. The volume of this intricate, jewel-like shape in a high-dimensional space is exactly the probability amplitude for that collision. The answer just falls out of the geometry. This is more than a neat trick, it's a profound clue. It suggests our most cherished assumptions, that events happen in a local spacetime, that particles travel from here to there, are not fundamental. They are derived, they emerge from something deeper. The amplituhedron's geometry is built on principles of positivity and consistency, pure mathematical principles with no reference to a background stage. Locality and unitarity, the ideas that things only affect nearby things and that probabilities must add up to 1, are not inputs, they are outputs, they are properties that fall out of the shape's geometry. It hints that the true bedrock of reality is not a vibrating fabric, but a timeless, placeless mathematical object, a static, perfect jewel. Our experience of a dynamic universe of cause and effect unfolding in time is a kind of shadow this jewel casts. A profound and useful illusion that our consciousness interprets as a sequence. We are like viewers who only see the two-dimensional shadow of a three-dimensional sculpture, mistaking the complex dance of shadows for the true, solid object. So when physicists at the Large Hadron Collider smash protons together and sift through the debris, the underlying truth of that event might not be a story of quarks and gluons moving through the void. It might be a single, immutable fact inscribed in the geometry of an amplituhedron. The fabric isn't being woven or computed in those moments, it is being revealed. As a consequence of a deeper, more serene and absolute mathematical reality, if our dynamic world is a shadow of a timeless shape, what casts that shadow? The answer might lie in the very act of observation, in a blueprint where consciousness itself becomes the weaver. The amplituhedron has this timeless, serene geometry. But the universe isn't always serene. There are places where reality gets pulled to its absolute limit. The 21st blueprint isn't really a blueprint. It's a paradox, a violent contradiction. It says the smooth fabric of spacetime has to tear itself apart. The black hole firewall paradox. It starts with a simple principle from Einstein. The equivalence principle. If you're falling into a black hole crossing the event horizon, you shouldn't feel anything, no jolt, no marker. The horizon isn't a physical wall. It's a point of no return for light, but for you, falling freely, it would be uneventful. Space would seem smooth. That's the foundation of general relativity. But quantum mechanics has a different rule, a sacred rule called unitarity. Information can't be destroyed. It can be scrambled but never erased, and for decades there was this puzzle. When something falls into a black hole, what happens to its information? Stephen Hawking showed black holes evaporate. They radiate away their mass. If the black hole vanishes completely, does the information vanish with it? That would break unitarity. For years, the idea was the information was encoded in the Hawking radiation. A subtle, complex encoding, leaking back out. Then in 2012, physicists Ahmed Almary, Donald Marolf, others, they turned that story on its head. They did a careful thought experiment. They assumed three things we really want to be true. 1. Information is not lost. 2. Physics outside the black hole is normal quantum field theory. And 3. Nothing dramatic happens at the horizon. The equivalence principle holds. Their conclusion was shocking. You can't have all three. The assumptions are inconsistent. Something has to give. Their math suggested if information is preserved, the horizon can't be the quiet place Einstein predicted. Instead, it has to be a searing wall of fire, a firewall, an energetic barrier where an infalling observer would be incinerated instantly. The smooth fabric of spacetime would violently break down. That's the paradox. To save quantum mechanics, you have to sacrifice the smooth geometry of general relativity right at the edge of a black hole. The firewall isn't a proposed object. It's a signpost of inconsistency, a crisis. It forces the question, which principle is wrong? Is information truly preserved? Could it be lost? Or is our understanding of the horizon flawed? This paradox is a crucible. Every blueprint strings, loops, holography, emergent gravity has to face it. Can it resolve the firewall? Can it show how the fabric can be smooth for a falling observer and still preserve information? The answer might be that our idea of locality is the mistake. The idea that you can point to a single place like the horizon and ask what happens there. In holography, for instance, the interior of the black hole is a projection. The real information never crosses a local horizon. It's painted on the surface. The falling observer's experience is a computed illusion. The paradox dissolves because the question was asked in the wrong language. Other theories suggest the fabric has a quantum structure so fine that a sharp horizon is meaningless. Like trying to pinpoint the exact surface of a cloud, this paradox isn't an end, it's a beacon. It illuminates the precise point where our two great theories clash. A storm of logical contradiction. It tells us the true fabric of reality must have features we haven't imagined, features where smoothness gives way. Not to infinite curvature, but to a fundamental restructuring of cause, locality, and information itself. The firewall is a tear in our current maps. And through that tear, we might glimpse the outlines of a deeper truth. That firewall paradox, it pulls at our maps, but the fabric itself is doing something bigger. More relentless, the 20-second blueprint is the dark energy puzzle. The universe isn't just getting bigger, it's stretching faster and faster. This isn't a slow drift. It's an acceleration. Something we can't see is driving it. Dark energy, a kind of pressure right in the vacuum of space. It's a repulsive force. It pushes galaxies apart, and that push gets stronger. They found this by looking at distant supernova. It was a shock. Teams, Adam Rees and others, they thought they'd see the expansion slowing down. All the gravity from all the matter. It should have been breaking the whole thing. But they saw the opposite. The expansion is speeding up, like throwing a ball up and watching it just take off. As if gravity flipped. For that, Rees won the Nobel Prize. The scale of it is hard to grasp. Dark energy is most of the universe now, about 70% of everything. The stars, the planets, the galaxies, all the normal matter and the dark matter we talk about, it's just a fraction. The cosmos is ruled by this silent, expansive tension. So think of spacetime not as a passive sheet. It's a canvas that stretches itself. Dark energy is the tension in that canvas. A property of empty space that makes it repel itself, and that changes the final fate of everything. The main picture now is a cosmic heat death. This accelerating expansion will stretch the fabric so thin that galaxy clusters become isolated. Then galaxies themselves, over trillions of years, stars go dark, black holes evaporate, the universe becomes a vast, cold, nearly empty void. The temperature drops almost to absolute zero. A silent, frozen equilibrium. This accelerating canvas, it implies the fabric has a kind of memory, a cosmological constant. Einstein thought of it, then threw it away. A fixed energy density of the vacuum, or maybe it's something that changes, a field that evolves. Whatever it is, dark energy is now the main architect. It shapes cosmic geometry on the largest scales. It decides the future curvature of everything we can see. It's the silent driver, the background hum of creation that, in our time, has taken over. So when you look at the night sky, you're not seeing a static tapestry. You're watching an active, accelerating artwork, an expanding canvas where the threads of space are being pulled apart by an invisible hand. The question it leaves is haunting. Is this acceleration permanent, a feature of the fabric itself, or is it just a phase in a longer, more complex story? The answer decides more than the fate of galaxies. It decides the ultimate meaning of structure in a universe that seems set on dissolving it. A timeless universe seems impossible. But the 23rd blueprint makes you face it, the Wheeler-DeWitt equation. It comes from applying quantum mechanics to the whole cosmos, to the geometry of space. And when you do that, the time variable just vanishes. It's gone from the equation. What's left is a description of the universe as one static quantum state. A frozen wave function of everything. That's not an error, it's the point. John Wheeler and Bryce DeWitt developed this. It suggests that at the most fundamental level, the universe doesn't change. It just is, an eternal now. All possible configurations of space and matter and energy are superimposed in that one state. So then, where does our experience of time come from? The flow of seconds, stars aging, history unfolding. The answer is in correlations. Think of a vast, complex clock. All its gears and springs are fixed in one position. But if you only look at a few gears and compare their positions to each other, you can define a sequence. One gear's position relative to another becomes your clock. Change is an illusion of perspective. It's what you see when you, as a small part of the universal wave function, interact with another part. Your consciousness, your measuring devices, they don't see the whole frozen picture. They see correlations between parts, and you interpret that sequence of correlated changes as the flow of time. Wheeler-DeWitt saw this as a profound shift. Time isn't a river the universe floats on, it's a story we tell ourselves, a narrative built from the relationships between things inside the universe. In this view, the Big Bang isn't an event in the past, it's a feature of the wave function, a particular correlation that we, from our limited viewpoint, experience as a beginning. This solves a deep problem in quantum gravity, the problem of time, but the price is heavy. It asks us to let go of time as a fundamental ingredient. The fabric isn't a dynamic, flowing entity. It's a static, breathtakingly complex tapestry, and we are patterns within it, mistaking the intricate weave for motion. Our entire lived experience, from first breath to last, becomes a single, elaborate stitch in that eternal fabric. A stitch that only feels like a journey because we can't see the whole, completed work. A timeless universe seems to contradict everything we experience. But the search for its nature always brings us back to the light we can see. The 24th blueprint is the phenomenological approach. It doesn't begin with a grand equation. It begins with the evidence, the subtle fingerprints left on the cosmos. It pieces together a picture of the fabric from the top down, using the only clues we have: the light that's traveled across the eons to reach us. This is detective work on a cosmic scale. Instead of assuming a fundamental theory and predicting what should happen, phenomenology asks what the universe is already telling us. It looks for tiny deviations, minute cracks in our standard models that might show the underlying texture of reality. One of the most powerful probes is light itself. Especially the most energetic light, gamma-ray bursts. These are colossal explosions from the distant universe, sending photons across billions of light years. In our smooth, classical picture of spacetime, all photons should travel at the same speed, the speed of light. That's Lorentz invariance, a cornerstone of Einstein's relativity. But if spacetime has a granular, foamy structure at the Planck scale, like a quantum foam or a discrete lattice, then that foam might act like a subtle medium. Higher energy photons, with their shorter wavelengths, might interact with this fine-grained structure differently than lower energy photons. They could be slowed down ever so slightly. Over cosmic distances, that tiny delay could accumulate into a measurable lag. So when a distant gamma-ray burst flashes, telescopes on Earth watch for a time difference between the arrival of its highest energy gamma rays and its lower energy ones. Finding such a lag would be a direct signature of spacetime's granularity, a whisper that the fabric has a grain. So far, the light tells us no such delay exists within our current precision. The fabric appears smooth to these incredibly sensitive tests, but the search continues, pushing to greater distances and higher energies. Another window is the cosmic microwave background. The afterglow of the Big Bang. This ancient light is a snapshot of the universe when it was just 380,000 years old. Imprinted on its subtle temperature variations could be echoes of quantum gravity processes from an even earlier epoch. Some theories predict specific statistical patterns, non-Gaussianities, that would be a smoking gun. The Planck satellite and future observatories are scouring this cosmic blueprint for any such anomalies. It's like examining a vast, fossilized ripple in the fabric of space. looking for imperfections that reveal the material it was made from. This empirical stitching also includes laboratory experiments. Exquisitely precise atomic clocks are monitored for tiny, spontaneous fluctuations in their tick rates. The idea is that if spacetime is foamy, it might introduce a fundamental uncertainty in the flow of time itself, causing clocks to jitter in a characteristic way. Others look for anomalous noise in gravitational wave detectors or subtle shifts in the spectra of distant quasars. This blueprint is a necessary anchor. It grounds our theoretical speculations in the hard soil of observation. It reminds us that the true nature of the fabric won't be decided by mathematical beauty alone, but by a consistent story told by the data. A story written in the delayed arrival of gamma rays, the statistical whispers of the microwave background, and the steady tick of an atomic clock. We're building a portrait of reality not from first principles, but from its faint, persistent signatures. The universe is leaving clues. Our task is to be patient, meticulous collectors, stitching each one into a map of the ultimate architecture. That patient listening to the universe, that whole search, it brings you to a final question. Why does the fabric we measure seem so hospitable? This last blueprint isn't about equations. It's about perspective, the Anthropic Principle. It says the constants in our cosmic tapestry, gravity's strength, the electron's mass, the amount of dark energy, they aren't random. They fall in this razor-thin range that allows for stars, for planets, for observers. We couldn't be here asking these questions if those numbers were even slightly different. With slightly stronger gravity, stars burn out in millions of years, not billions. No time for life, a weaker nuclear force, and hydrogen never fuses. Stars never ignite. The fabric looks finely tuned, almost like it was expecting us, and that observation starts one of the biggest debates in cosmology. Is this tuning evidence of purpose or just a colossal fluke? The principle gives a starkly logical answer, especially with a multiverse. If eternal inflation makes a near infinite number of bubble universes, each with random laws and constants, then it's no surprise we find ourselves in one of the rare bubbles where the numbers line up. Leonard Susskind argues we shouldn't be amazed to find ourselves in a life-friendly universe, any more than a fish should be amazed to find itself in water. It's the only place it could be. Our presence acts as a filter. It narrows all possible realities down to the single slice that allows us to exist. But critics see this as a conversation stopper. A tautology, a kind of cosmic survivorship bias. They say it risks halting the search for a deeper reason why the constants have these values. Why should the multiverse landscape favor life-friendly bubbles at all? The principle doesn't answer that. It just notes our inevitable location within one. Yet even as a meta blueprint, it adds a crucial layer of context. It reframes the quest. We aren't just studying an impersonal fabric. We're studying the specific, rare conditions that allowed that fabric to become self-aware. The emergence of consciousness isn't a random accident on a neutral stage. It's a potential written into the architecture from the start, a possibility that needed a very specific weave of space, time, and constants to become real. Our curiosity about the cosmos in this light is the universe's way of understanding itself. The finely tuned stage and the conscious audience are part of the same phenomenon. So as we map these 25 blueprints from bending geometry to timeless shapes, we're tracing the contours of a reality that isn't alien to us. We are its most intricate expression. The search for the fabric's final blueprint is also a search for our own deepest origins. There are 25 different maps, all trying to describe the same place. A place we've never seen. It's a geometric warp, a quantum foam, a hologram, a cosmic crystal. You put them next to each other and you start to see patterns. Threads that run through all these different ideas. The first thread is emergence. Our reality, the smooth space and time we know, isn't the base layer. It's something that comes out of something else, a collective effect, a story that gets told, whether that something else is a quantum network or a sea of information or just a simple rule being run. The message is the same. The stage isn't built before the play. The actors build it scene by scene just by interacting. The solid world is an illusion of scale. A second thread is discreteness, the smooth continuum, the idea of infinite division. It seems to break down. At the very smallest scale, reality looks granular. Pixels of space, quanta of time, separate events. This graininess isn't a mistake, it's a feature, a fundamental limit that stops the infinities in our math. It gives spacetime a texture, an unimaginably fine one. The universe might be like a pointillist painting, from far away a seamless picture, up close just dots. Then there's information. What is reality made of? The answer seems less like matter or energy and more like data. The universe computes, it processes. The laws of physics might be the algorithms. Space-time and particles are just the stable patterns that come out of the computation. The holographic principle takes this further. It says all the information inside a volume is actually painted on its surface. We're not just made of atoms, we're made of bits. The story is written in quantum yes or no questions. And then there's the thread about entanglement and geometry, spooky action at a distance. That's not just a weird quantum thing anymore. It's seen as the glue that holds space together. The ER equals EPR idea. It says every entangled pair of particles is connected by a tiny wormhole. Geometry isn't the stage for entanglement, it's built from it. Cut the quantum links and the idea of here and there might fall apart. So which of the 25 is right? The goal isn't to pick one winner, it's to find a synthesis. Each one is a different view of the same mountain. General relativity describes the slopes we can see. Quantum theory probes the rock underneath. They're not contradictory. They're complementary, they constrain each other. A real theory of quantum gravity has to show how Einstein's smooth geometry comes out of a discrete quantum base. It has to show how entanglement creates curvature. It has to solve things like the firewall paradox. The true map will probably have pieces from several of these sketches, combined into something we haven't fully imagined yet. This synthesis, it's more than a scientific project. It shows how creative the human mind can be. Faced with the biggest mystery, the architecture of everything, we didn't give one answer. We gave a symphony of them. Each blueprint, whether it's elegant or outrageous, is a leap of intuition. An act of imagination, trying to decode a universe that works by rules far stranger than our daily life. The value of this, it's in the questions we've learned to ask, as much as in any final answer we might find. Because when we question the fabric of reality, we're really exploring the nature of our own understanding. And our place inside the vast tapestry we're trying to describe. Our journey through these 25 maps shows a cosmos of staggering possibility. The universe isn't a simple, static stage. It's a living question, a dynamic process, a story being written in the language of geometry and information and quantum connection. We started with Einstein's elegant warping of the continuum. Then we descended into the seething quantum foam beneath it. We saw space crystallize from a graph. We watched reality project from a holographic screen. We even glimpsed timeless shapes like the amplituhedron that suggest our whole narrative of cause and effect is a kind of beautiful shadow. The takeaway is that space and time aren't fundamental ingredients. They're not the canvas, they're the painting, an emergent masterpiece. It arises from deeper, stranger principles, relationships, data, the ceaseless hum of quantum events. Physicist Carlo Rovelli reminds us we aren't permanent stuff. We're patterns, fleeting, intricate configurations in a network of processes. We perpetuate ourselves just long enough to wonder about the weave of the tapestry we're part of. This changes everything. It means our quest to understand the cosmos isn't a distant observation. It's a participatory act. Our consciousness, our science, our art, they're the universe becoming aware of its own architecture. So let this expedition be a beginning, not an end. Let it ignite a personal curiosity. Which of these blueprints feels most compelling? Does the idea of a holographic universe resonate? Or does the crystalline structure of loop quantum gravity seem more tangible? Maybe the minimalist beauty of causal sets speaks to you, where reality is just a story of cause and effect. The conversation is what matters. It's how we, as a pattern-seeking species, refine the map. Share your thoughts. Which theoretical sketch of reality feels most true to the universe you experience? Subscribe for more journeys to the edge of understanding, where science meets the profound, and always keep looking up at the starry expanse and inward at the boundless mystery within. Because in questioning the fabric of everything, we ultimately discover more about the wondrous pattern that is us.